Okay, right. Good evening all. Can you confirm whether I'm clearly audible and visible? Okay, it's fine, right? It's working fine, right? Okay, right. Okay then, okay. Right. We'll start. Right, we'll start. Right. Okay then. Right. So good evening again. So about today's session, right? This is something we are starting in today, right? Something we are starting in today, and in these sessions, my main focus is essay questions. Right? In these sessions, my main focus is essay questions, and mainly, uh, I need to recall the writing essays, and you will be practicing essays. Some essays you will write here with me, and when you are writing, I will recall the theories and the other background that you need meanwhile, right? When the question goes, and again during the discussion, I'll be sharing the other tips and tricks, right, that we are using when we are writing essays, that we are using when writing essays, right? Like tips and tricks, right? Those are like very important things at this stage, because we are like 25 days from the exam, 25 days from the exam. So we are getting closer to the exam day by day, right? And this is the time that you can polish up the things that you have learned, right? So I know you are writing papers now, and you are practicing questions, right? Studying, doing structured essays, right? So there are kind of workload goes on these days, right? And about this session, right? Don't take this as a burden or something, right? This is something that you can join in a relaxed manner, right? In a relaxed manner. So after all work is done, this time that we are taking maybe a time between 1 hour to 1.5 hours, right? Something like that. So spend this time effectively as a relaxing time, right? Otherwise, I don't want to make this a burden again as just as a class, right? Just as a class. So therefore, don't take this as a burden or something, right? Don't take this as a burden or something. You can freely attend the session and get what you need. Right, about the questions, I have already uploaded the questions, and I think some of you might have tried the questions. And if there's anyone who couldn't get the questions, right? If there's anyone who couldn't get the questions, I will put the link again to the chat. Give me 1 second. Right? I can put the link again to the chat. So if needed, you can go here and get this, right? If needed, you can go here and get this. If you haven't get the Tutes yet, Tutes means there are 3 questions there that I'm planning to go through today, right? Give me 1 second. So basically, about the lesson, right? About the session, right? Basically about the session, right? Our main focus will be essays, and this is something I do uh, except S2A discussions going on, right? This is something I do except S2A discussions going on, right? And for the S2A now, usually on Thursdays I'm taking it for the S2A discussion, right? And for this week, since I'm taking this today on the Thursday, I'll be shifting the S2A for the week to maybe Saturday or Sunday, right? I will let you know right? Probably it can be a Saturday. Probably it can be a Saturday. It can be Saturday, right? Right. Probably it can be Saturday anyway. Sorry. Probably it can be Sunday, not Saturday. Sorry. Probably it can be Sunday for this week, right? So I would link here, and right, I have pinned it. If you haven't got it yet, if you haven't got the questions yet, right, what you can do is you can visit those links and get it. All right, then, yeah. So here I'll be taking the special types of essays, right? Special essays we have in our paper, right? Especially the essays that you can score easily, but yet uh, students are struggling, right? We know we can score very easily when it comes to such essays, but for some reasons they are like there means students are kind of fear of taking these essays, and sometimes they don't know the exact theories. They have a kind of a fear of taking the question, right, because of the uncertainty of theories, and sometimes the correct techniques of doing the question they don't know, right, correct ways of approaching, right. Now today I have selected electronics. Today I have selected electronics, right, because I know, even though uh, most of you have got the theory coverage properly, right? You are kind of fear of taking these questions, right? Especially questions like electronics, matter and radiation, properties of matter sometimes, right? So likewise, right? But when it comes to questions like electronics, matter and radiation, right? They are comparatively easier types, right? Easier questions to score, but yet a less number of students are taking such questions, right? So kind of a gap is there, Yet they are sometimes quicker and faster questions to do and easily doable questions, right? But yet they don't take, right? So that's why I chose electronics today, right? Let's see how this goes, right? Let's see how this goes, and yeah, I will share with you the tips, tricks, and the other things that you need to consider, that we need to care about when you are writing these essays, right? Now, without any further ado, let's get into the thing, right? Let me share my screen first. Okay. Right. Is it visible now? Visible, right? Okay, screen is visible. Right. Listen about electronics and the first essay question we are going to discuss, right? First part of this first essay is from facts, right? First part is from facts, right? I will quickly recall the background you should know about facts first, right? Quickly, and you will get to know the other things, right? Other things means the special things and the additional details, right? Additional details uh, as this goes, as the discussion goes, right? Api discussion at the all right. Then uh, let's see. First thing about FETs. FETs means field effect transistors. No? When it comes to FETs, you have two types, right? FETs. There are two types of FETs we have. One is NJ FETs, right? NJ FETs, N channel junction field effect transistors, and the other type PJ FETs, right? PJ FETs, P channel junction field effect transistors, right? NJ FET and PJ FET. Now, from these two, when it comes to questions, you are getting only questions in the sense for calculations, for sums, right? For sums, we are only getting from NJ FET, right? From NJ FET. So quickly, if I recall, NJ FET is something like this is the circuit symbol. Circuit symbol is like this, right? And this common terminal is called gate, and this is called drain. This is called source, right? Drain, gate, and source. And current flows here are, right? Current flows here, there are only two current flows. ID flows downward, and IS flows downwards. There are no currents in G, there are no currents through gate, and usually gate is grounded. Usually gate is grounded unless there is a voltage divider circuit. In voltage divider circuit, gate is not directly grounded. It can be different with the voltage. Right? Actually, in this particular question, what is given is a voltage divider circuit. Right? There is a voltage divider circuit. Since there is in the question, I will explain the other things about the voltage divider with that. Right? And here, one more thing, since there are only two currents, always ID equals IS about ID equals IS about a NJ FET, right? Or any kind of a FET circuit. ID equals IS, right? Now, let's start. Let's start about the first one, part A, right? First question, it's asked, why field effect transistors FETs are called unipolar devices? What are the charge carriers contributing to the operation of FETs? Right, unipolar. Unipolar devices means they operate only with, or they function only with, they work only with one type of carriers. Right, one type of carriers. In electronics, we have two types of carriers. No, right. In electronics, we have two types of carriers, either electrons or holes. Right. When it comes to bipolar transistors, if I compare this, when it comes to bipolar transistors, right, bipolar, you know, NPN and PNP. When it comes to bipolar transistors, they have majority carriers and minority carriers, right? Which means both carriers are contributing. Both carriers are contributing uh, the functioning of the transistor, right, or the operation of the transistor. When it comes to unipolar transistors, uni means one. No? Uni means one. That is the exact meaning. Uni means one. Then here only one type of carriers. It is either electrons or holes contributing the operation of this FETs. Right. That is why they call unipolar. Right. That is why they call unipolar. Then what is asked is why they are called unipolar transistors. Then you have to say that, right? Because only because only because either electrons or holes, because either electrons or holes are used as electrons or holes are used as carriers for the operation. Unipolar means one type of carrier is used, and other than that, there's one more thing. In bipolar transistors, there are two PN junctions, but in unipolar transistors, there's only one PN junction. In bipolar, there are two PN junctions. Right? In unipolar, there is only one PN junction. There is also another difference, right? Main difference we can see between these two. The main difference is this one, and the second main difference is about the number of PN junctions. Okay, then what are the charge carriers contributing to the operation of FETs? Right. Then for the first one, they are not asking for the electrons or holes, right? Then you are mentioning, if you have mentioned about just as only one type of carriers are contributing, that is enough. That would be enough, because only that is asked, right? Because either electrons or holes are contributing. Then for the second one, we can write as what are the charge carriers contributing to the operation of FETs? That is either electrons or holes. Either electrons or holes. Either electrons or holes. Right. Now, without writing or without mentioning specifically about electrons or holes, if you mention that just as one type of carriers, that is also enough, as how it is asked in the question. Right. Second one, state why FETs are also known as voltage control devices. Right. Here, the main difference is with, again, bipolar transistors. Bipolar transistors are called current control devices. Bipolar are current control, and unipolar are voltage control. The reason is this is controlled by VGS. What is VGS? VGS means voltage difference between, or the potential difference between gate and source. Like this, whole device is controlled by VGS. Right? Then write down this way. Device is fully controlled. Device is fully controlled by the voltage difference. By the voltage difference between between gate and source, right? That is called VGS. That is called VGS in our jargon. Right? In our jargon, we call it VGS. Right? Then third, calculate the drain current ID. This is the calculation part here. Calculate the drain current ID and the gate source voltage VGS for the circuit shown in the figure 1, assuming VD equals 5 volts. Assuming VD equals 5 volts. VD equals 5 volts. Now, this is D, right? This is D, and this is S, right? We know this is G. If this is G, this is VG, right? Then, if I mark the currents, ID falls downward, close downwards, and IS is downwards, right? And since this is a voltage divider circuit, this is called a voltage divider configuration or voltage divider circuit, right? Then if this current is simple, like let's say no current flows through G, then it flows like this, right? Then we can see same current flows through, right? Same current flows through what we call R1 and R2, and they are in the series combination. That is also noticeable, right? And what we need is VGS. VGS is here. Potential difference between G and S is here, right? Now, what we asked is ID. ID first. ID and VGS. To find ID, now VD is given. No, VD was 5. See, VD is given. This is 5. Then about RD, potentials at the two ends, two terminals of RD of the resistor connected to D is known, right? Which means you can apply delta V equals IR for resistor RD, right? Then this one, number 3, what we can do is for resistor DRD, delta V equals IR, right? Delta V equals IR. Then delta V is high potential to low potential 9 minus 5. 9 minus 5 equals ID RD is 2.2 kilo ohms kilo, right? Then that's a small simplification. ID equals 9 minus 5 is 4, then 4 over 2.2 10 to the power minus 3. 4 over 2.2 is 1.82. 1.82. Then this is 1.82 milliamperes. 1.82 milliamperes, right? The other beauty of FETs is, right, all FETs are simplified or they are solved mainly using delta V equals IR. Delta V equals IR or V equals IR, right? As specific equations for a FET, we have only one. That is also only for the normal configuration, not the voltage divider. For this configuration, all the questions are solved using V equals IR only, right? Then as the second part, it is asked about VGS, right? Then to find VGS, right? To find VGS, first we need VS, right? VS and VG. Then to find VS, we can apply delta V equals IR again for RS, right? For RS, delta V equals IR. Delta V across RS is, right? Now, if VDD is given here, this terminal is grounded. If VDD is given above, this is grounded. Right? Grounded means it is 0. Then this point is at 0. Then VS, we need VS. That is VS minus 0. IS is same as this, right? Same I told you before. 1.82 milli 10 to the power minus 3. 1 kilo ohm, then 10 to the power 3. And you better mention this logic here. Always ID equals IS. ID equals IS, right? Then these two cancels off. VS equals 1.82 milli. Sorry, VS equals 1.82 volts. 1.82 volts. 1.82 volts. Then I need VG. To find VG, what you can do is these two resistors are in a series combination. Right? I have to mention these logics. R1 and R2, right? Mentioning logics, right? Is a must you should do. It's a must thing you should do, right? So even though you are doing the question, right? If you miss mentioning these logics, you will lose marks. That's the thing, right? mention these things. R1 and R2 are in series combination. Are in series combination. Right? The reason is Ig equals 0. Reason is Ig equals 0. Right? R1 and R2 are in series combination. Then using voltage divider, that is also called potential divider. Using voltage divider, O will apply for the grounded one for R2. For R2. Then total potential difference across that branch is, if this is VDD, same wire up to here, this is VDD. That is same wire. Then that is 9. Then if this is 0, same wire up to here 0. Right? Then total potential difference is 9 minus 0. Total potential difference is 9 minus 0. Potential difference across my resistor is Vg, then Vg minus 0. Total is VDD minus 0 over R1 plus R2 into R2. Right? Apply the values here. Vg, I need to find Vg. Right? VDD is 9 minus 0, that's 9. No? R1 plus R2, 10 plus 2.2, 12.2. No? 12.2. Right? Times 2.2. Right? Simplify this. Right? Simplify this. Then it is coming as 1.62. 1.62 volts. 1.62 volts. Now our target was VGS. Our target was VGS. Then you can write VGS now. VGS equals VG minus VS. Right? VG is 1.62 and VS was 1.82. 1.82. Right? VGS is minus 0.2. Minus 0.2. Right? In any kind of effect, VGS is always minus. In any kind of effect, VGS is always a negative value, a minus value. Right? Then this is also a verification that you should get a minus value. Right? So we have got a minus value. Right? Kind of a verification. Right? So part 1 is done. And this part was given for 10 marks. This part was given for 10 marks. Right? That's nothing much to do, right? But 10 marks are given. Right, part B. Part B. Now, part B is about op-amps. Part B is about op-amps. Right, now in these selected questions, right, kind of target questions with a high potential this time are here, right? So that's why I'm discussing these ones, right? You better check these question types again and again and practice these question types again and again before you go to the exam, right? Different question types we have here, right? Analog, digital, bipolar transistors, unipolar transistors, then op-amps, diodes, Zener diodes, right? Rectifications, okay, circuits again, right? B. In the op-amp circuit shown in figure 2, each electromechanical switch SI, I equals 0, 1, 2, 3, is operated by applying an electrical signal DI, I equals 0, 1, 2, 3, right? Which can be high 5 volts or low 0 volts, right? High means 5 volts, low 0 volts. When DI is high, the respective switch SI will be closed. When DI is high, DI is high. If DI is given a high signal, right, then the respective switch is on, is closed. Closed means on. Otherwise, it will be open, right? Okay, then first one. Oh, wait. Sorry, the question is missing here, it seems. Some part is not clear. That's an error occurred with the compiling, right? Compile කරද්දී මේ part එක වෙලෙන්ට දාලා නැහැ වගේ. What's the question? Yeah, a small part is missing. So I will read out the question and we'll do, right? And this is actually 2019 level past paper question. right? Check the given questions with the past papers you have, right? Right? Check the given questions with the past papers you have, right? Method in questions. Yeah, that is not here. It's a mistake, typing mistake, right? Question one is asking, when D2 is high, find the current through the resistor 10R in terms of R. When D2 is high, right? Listen, D2 is high means D2 is on. Now switch D2 is this. D2 is connected to S2. Now this is going to be on, right? When I switch on karata, D2 is going to be on, right? And the current through resistor 10R is asked. Current through resistor 10R is asked. Current through resistor 10R is asked. Right. Now, see what's happening. Now this is given as -5. This is given as -5 here. -5. Then if there is -5, this is the same wire. This is -5 here up to here. Right. And this is grounded. This is grounded. So we know we have golden rules for op-amps. Golden rules. Right. One golden rule is there are no current inflows through the input terminals. There are no current inflows through the input terminals. One golden rule. Right. And the second golden rule is if the op-amp is feedback. What is feedback? Feedbacking means if the output is connected back to one of the input terminals of an op-amp, that is called feedback. Right? That is called feedback. If the op-amp is feedback, V1 equals V2. Right? If the op-amp is feedback, V1 equals V2. V1 is the notation for the non-inverting voltage terminal +1, right? And V2 is the notation for the inverting voltage terminal -1, right? Then if this is 0, this is a feedback circuit. Since there is a feedback circuit, if this is 0, V2 is also 0 because in a feedback circuit, V1 equals V2, right? You have to mention these logics. They are the logics, right? These are the logics that you are given marks, right? These are the logics you are given marks, golden rules, right? You have to mention, right? First golden rule, you have to mention it when you are answering, right? First golden rule, you have to mention that there are no current inflows. There are no current inflows through input terminals. There are no current inflows through input terminals. So when we write all of them at the beginning, that is easier. Right? Otherwise, with the question or with the part that you are trying also you can do. Right? But when you have written everything at the beginning, then again you don't need to write it again and again. That's it. There are no current inflows through input terminals. Right? And the second one, V1 equals V2 when op-amp is feedback, right? These two are called golden rules, right? These two are called golden rules, right? Now, for this one, I have to use V1 equals V2 thing. Then V1 equals V2 equals 0 volts here. V1 equals V2 equals 0, right? The reason is golden rules. The reason is golden rules, right? Now check the circuit. Now this side is at 0, right? This side is at 0. If this is 0, V2 is also 0. This is 0, right? This is 0. Now, what's the question asked? Current through resistor 10R. Now, if this is 0, this is the same point up to here, that is 0. Then potential difference across 10R is known. Apply. Delta V equals IR for 10R, right? Then for 10R, apply delta V equals IR. Delta V is now current flows in this direction from high voltage to low voltage. Then potential difference is 0 minus -5. 0 minus -5, right? Otherwise you will get a minus current. That would be wrong. Then let's say that current is I, R is 10R. Then I equals 5 over 10R, right? That is 1 over 2R. So the current is 1 over 2R. One over 2R, right? Next, if a set of voltages, second one, see, if a set of voltages 5 volts, 0 volts, 5, which means 5 means high, no, right? 5 means high. simultaneously to operate switches S3, S2, S1 and S0. Right. Now this operation changes. See, now this operation changes. Now again you have to check what are the switches that they are going to be on and what are the switches going to be off. Right. Now we have to check what are the switches going to be on and off. Right. Let's see. Okay. See. Now 5 volts is given for S3. Then S3 is on. S3 is on. And 0 for S2. Now S2 is closed. And the other two are also on. S1 is on. S0 is on. S1 is on. S0 is on. Right. Then what is asked is calculate the current capital I indicated in the figure. Right. Now what we know is, right, there are separate current flows through these ones. No, say this is I3 and say this is I2 and say this one is I1. Right. Then we know from Kirchhoff's laws, this capital I is I1 plus I2 plus I3. Then if I find I1 plus I2 plus I3, right, one way is you can get that capital I. That is one way. Or else the other way is we can clearly see these three resistors are in a parallel combination. These three resistors are in a parallel combination. Right? These ends are at -5. And all these ends are, if V1 is 0, V2 is 0, no? All these ends are 0. All these ends are 0. Since they are in a parallel combination, first I'm going to solve this equivalent resistance. That is easier. Right? Now, without doing the equivalent, if you found the currents separately and if you do that way, that is also fine. That's up to you. That's up to you. I'm going to solve the equivalent. Right, then 1 over R equals, now functioning resistors are 1 over 5R plus 1 over 20R plus, right, they are parallel, no? 1 over 40R. 1 over 40R. Right, then 1 over R equals, right, say this is R dash equals, common denominator is 40R, 5 times 8, 20 times 2, this is 1. Right, then R dash equals 40R over 11. R dash equals 40R over 11. Equivalent is known. Now for the equivalent resistor, you can apply delta V equals IR. That is easier for me. Right? For R dash, for the equivalent, delta V equals IR. Right? For the equivalent, delta V equals IR. Delta V is 0 minus minus 5 again. Right? Same thing. 0 minus minus 5. Right? Capital I. Now the total current is coming at once because I am applying the equivalent resistance. R is 40R over 11. 40R over 11. Then this is 5 equals I times 40R over 11. 5 times 8 here. Right? Then this I equals 11 over 8R. 11 over 8R. Right? 11 over 8R. 11 over 8R. Right? Next, calculate the output voltage V out when the set of voltages 5, 5, 5, 5 is applied simultaneously to operate switches. Right? If all are 5, which means all switches are on. No? Right? If all are 5, the meaning is all switches are on. If all switches are on, all resistors are going to function now. Right? Part 3. If all resistors are going to function, now the equivalent changes again. Right? Equivalent changes again. Now this is also going to be on. Now I need the new equivalent. Right? I need the new equivalent again. Right? Say 1 over R double dash. That is given by 1 over 5R plus 1 over 10R plus 1 over 20R plus 1 over 40R. Now again, common denominator is 40R. Right? Common denominator is 40R. This is 8 plus 4 plus 2 plus 1. Then R double dash is 40R over, right? 8 plus 4, 12. 8 plus 4 is 12. 8 plus 4 is 12. 14, then 15, no? Right? So that is 40R over 15. 40R over 15 is, by 5 it cancels, right? 8R over 3. That is 8R over 3. Right? 40R over 15. Now that is 8R over 3. By 5 it cancels. 5 times 8, 5 times 3. Right. Now, again, for that equivalent, we can use the same thing, delta V equals IR. Then for R double dash, delta V equals IR. Still delta V is 0 minus 5. Voltages are unchanged, right? Potentials are unchanged, voltages are unchanged. Then 0 minus 5. We need this current into new R. R is 8R over 3. 8R over 3. Right? Then now from this we can find the current. If the current is known, right? If the current is known, we can find V out, because my final target is finding V out. Final target is finding V out. It is also about calculate the output voltage V out. If the current is known, now I is 15 over 8R. I is 15 over 8R. Current is known. Then what you can do is to get V out, apply delta V equals IR again for 8R. For 8R, delta V equals IR. Right? For 8R. Then through 8R, this is how this current flows. Through 8R, this is how this current flows. Right? From high voltage to low voltage. Then V out minus 0. It should be written as V out minus 0. Right? And current is 15 over 8R. 15 over 8R into R is 8R. 8R to 8R cancels. Then V out equals 15 volts. Final answer. Right? V out equals 15 volts. So again, not a big deal, right? I'm just applying delta V equals IR accordingly, right? Just applying delta V equals IR accordingly. When you do a question from op amps, right? Must know thing is golden rules, right? Must know thing is golden rules, right? So without knowing golden rules, you can't touch these questions, right? I recalled you the golden rules, right? These are the golden rules. There are no current inflows to input terminals, right? That is one, because resistance is too high at the input terminals, right? We discussed in the theories clearly. And if the op amp is feedback, V1 equals V2, right? Golden rules. And how to use these golden rules accordingly when solving questions, right? How to use the golden rules accordingly when solving questions, right? Then the next part here. Part C here is given in digital, right? That is a digital part. Digital circuit given, or the digital question is given. A cash operated snack dispenser will provide the pack of Mari or chocolate cream biscuits under the following conditions. Right. First one, the correct amount of cash is inserted. I. Mari or chocolate cream is selected. MOC. Right. If Mari is selected, availability of Mari in the dispenser. If chocolate cream is selected, availability of chocolate cream in the dispenser. Why? Right. First one. Obtain a logic expression. The logic expression for the conditions under which a pack of biscuits may be obtained. Right. A pack of biscuits, no? Which means now with these words get the idea. With these words get the idea. A pack of biscuits means that is about Mari or chocolate, no? Mari or chocolate, there is a O connection. Right? O connections. O connections are plus connections. O connections are plus connections. Then I need to focus on Mari or chocolate. Right? First, let's see the conditions that I need to satisfy to obtain Mari. Say FM. Right? Output that I need to obtain Mari is FM. Then to get the Mari biscuit, as a first thing, you have to insert money. Right? Have to insert money. I have to insert money. And Mari should be there. Mari should be selected. And Mari should be selected. And Mari should be selected. No. N means dot connections. Then dot Mari should be selected. M. Then correct amount of money is inserted. And Mari should be selected. And the order you have to just check whether it is an O connection. Right? And Mari should be selected. And Mari should be available. Right? O Mari should be available. Right? There's no meaning if O Mari should be available. Correct amount of money is inserted. And Mari should be selected. And Mari should be available. Another N connection. Then IMX. To obtain a Mari, right? If IMX are satisfied, we can obtain a Mari, because correct amount of money is inserted and Mari is selected and Mari is available. Similarly, if you need to obtain a chocolate cream, say FC, right? Say FC, then still correct amount of money should be inserted and chocolate cream should be selected. C. Chocolate cream should be selected and chocolate cream should be available. Chocolate cream or chocolate biscuit should be available. Chocolate cream biscuit should be available. Right? Then I see why. They are connections. And about the overall output, we know we need either Mari or chocolate. Mari or chocolate or connection. Then combining these two, the final output is going to be, right? Final output is Mari or chocolate. O means plus connections. Then F is, this is IMX and this one is ICY. Right? You can see I is common. Take it out. Then MX plus CY. Right? Then the final output is this. Right? Final output is this. If you didn't get this at once, you can have a truth table and check these values as well. Right? That is also a possible option. Right? That is also a possible option. But if you didn't get this at once, have a truth table and check it out. That's also fine. That's fine. Right? That's fine. But same marks are given. It will take a little bit more time than this, right? But still you can get the correct answers. If you didn't think of it at once like this, right? Still to get the correct answer, you can use a table. Second part, show how this may be implemented using logic gates. Right. Then drawing a logic circuit, digital circuit for a given output. Right. Logic drawing a digital circuit for a given output. Then outputs are inputs are I, M, X, and CY. No, right? There are five. There are five. Then if my inputs are here, right? If my inputs are here, I, M, X, C, Y. I, M, X, C, Y. Right? So first I need IMX. Then first I need IMX. Right? I is here. Right? Take M from here. Take X from here. Right? And this is IMX. Right? This is IMX. And for ICY, the other one is ICY, no? IMX and ICY. Right? IMX, there are different possible circuits. Then for the other one, ICY, right? This is ICY. And the O of these two connect with the O gate. This is F, right? Or else, if you are plotting this for this output that I obtained here, right? Or else you can do it here. Then for this output, F is I times MX plus CY, no? Right? For that one, again, if wires are like this, sorry, if input wires are these ones, right? First I need MX, then IMXCY. First I need MX. Right? There are like 4-5 possible circuits here, right? For any circuit, marks will be given. MX, then MX is here, then CY is here, right? These two should be plus, then O gate, and from this the addition comes out, and with I it should be dot, then take I from here, right? And you can connect an AND gate here for the dot connection here, right? That's it. So likewise, there are different circuits. That's up to you. And for any correct circuit, total marks will be given. For any correct circuit, total marks will be given. For any correct circuit. Right. That's it about that question. Yeah, that's it about that question. Right. Now, about electronics, the benefit that we have is you can score this in a quick time. Right. You can score these marks in a quick time. Right. That is the main benefit we have. Right. If we are spending like say 30 minutes, 35, 40 minutes for a question like mechanics, thermal, right? Maybe electricity, right? Now in these things, in these questions, the benefit is you can score in a quick time. Right? That's the thing. Right. Then Question 2 is also an op amp. First part is an op amp. Second part is connected with the flip flop. Right. Second part is connected with the flip flop. Right. Before question 2, I'm going to go with question 3, because in question 3 there is a diode and Zener diode question, basically diode question. Right. I discussed about op amps here in this one also. No. Then here we'll see something. See the things about diodes. Right. Diodes check कर ले. Go to question 3. Go to question 3. Right. It says 200 volts RMS. What is RMS? Root means square wave. RMS. 50 hertz sinusoidal main power supply is connected to a primary coil of a step down transformer with turns ratio 20 to 1. With turns ratio 20 to 1. Right. Then the secondary coil feeds a full wave bridge rectifier with ideal diodes, followed by a smoothing capacitor C and a Zener diode voltage regulator as shown in the circuit diagram. Right. Now, to answer this type of question, overall you have to know all the electronics. Right. Overall you have to know all the electronics. You have to have a good general idea, good idea about electronics. But if you know everything, easily you can write. Right. That's the thing. If you know everything, easily you can write. Right. But if not, right? Sometimes you might get stuck in the middle of the question. Right. Then 3. Then it says circuit diagram. Right. Now the circuit is given, and basically once we saw the circuit, right, what should comes into your mind is our rectifier circuit, full wave rectifier. Right. What should come into your mind is full wave rectifier. Right. This is the exact same circuit as the full wave rectifier. Right. Let's see. First one. Calculate the RMS. Calculate the RMS, VRMS, voltage and peak voltage VP across the secondary of the transformer. Take root 2 as 1.4. Okay. Then RMS is asked. What is given here? 200 volts. That is also RMS. Right? 200 volts is also RMS. And VRMS is asked. Right. So we know VRMS equals Vmax. Vmax means VP. Both are same. Vmax, maximum value or peak value. VRMS is Vmax over root 2. VRMS is Vmax over root 2. Right? Then VRMS given here is 200. VRMS given here is 200 equals Vmax. Right? Vmax is also called VP. Right? Then this is Vmax over root 2. Now Vmax of this first coil is 200 root 2. Vmax of the first coil is 200 root 2. Right. Now using the transformer, you can find the output voltage or the V2 of the secondary loop, secondary coil. Then equation of a transformer is this, right? The equations V1 no V2 equals N1 no N2 for a transformer. V1 no V2 equals N1 no N2. Then V1 is 200 root 2, right? And I'm going to find V2. N1 to N2 ratio is given as 20 to 1. That is given as 20 to 1, right? Then 20 simplified, 10 remains. Then it says V2 equals 10 root 2, right? Now we need RMS value at the secondary coil. No? Again, VRMS equals Vmax over root 2. Then VRMS equals Vmax for the secondary coil is 10 root 2 over root 2. Root 2 cancels. Then VRMS equals 10 volts. Final answer 10 volts. Right? VRMS equals 10 volts. And then VRMS voltage and peak voltage, VP. And VP is also asked. VP is here. VP is, we do know. Then VP equals 10 root 2, right? 10 root 2 is given as 1.4. That is 14 volts. Right? 14 volts. Right? Well, first calculations are these two. First two are these two, right? RMS calculations. RMS calculations. Second one. Second one. Draw the shape of the voltage waveform at the output of the full wave with rectifier without the capacitor and Zener diode. Right? Without the capacitor. Without the capacitor. If there is without the capacitor, there is no smoothing. If there's no capacitor, there's no smoothing. If there's no capacitor, there's no smoothing. If there's no smoothing, right? What happens is only the rectification takes place, right? Rectification. Rectifier and there's no smoothing. Then from the rectifier, right? This is how the input voltage is rectified, right? Now these are the parts we have covered in theories. These are the parts we covered in theories. Otherwise, now you can't do all the things when the question is here. Right? You have to know the shape. But that is not the thing when it comes to questions. Right? That is not the thing when it comes to questions. And when you draw this, minimum, you have to draw like 4 loops. Minimum of 4 loops. Minimum. Right. Then 3. What is the frequency of the output voltage of the full wave bridge rectifier? Right. Now, if I give the idea here, right, the input signal variation is like this. No, input signal variation is like this. We have drawn all these things in the note, right? Input variation is like this, right? Now here it says the frequency is 50 hertz. It says frequency is 50 hertz, right? Now when that is rectified, what has happened is something like this. No, now the vibration is only this. And during the same time interval, now 2 vibrations takes place. Now initially it was only 1 vibration. See? That was only 1 vibration, 1 oscillation or 1 vibration. And now it is 2 vibrations during the same second. Now initially if it was 50 hertz, now it should be doubled. That is 100 hertz. Right? To get the idea, I just showed you these curves. Right? So therefore here it should be 100 hertz. Answer for the third one is 100 hertz. Number of loops are doubled over the number of vibrations. Number of oscillations are doubled. Since number of oscillations are doubled, right, frequency is doubled. Frequency is number of oscillations, so number of vibrations per second, no? Right, that is a per second value. Next, 4. How a full wave rectifier different from a half wave rectifier? In half wave rectifier, right, the output you are getting is this. In a half wave rectifier, the output we are getting is this, right? Like this. Exactly half of the wave is cancelled off, right? Exactly half is cancelled off. Then the question is about how full wave rectifier is different. Then what's the difference? Difference is both halves are utilized here, right? No half is going to cancel, right? No half is going to cancel. Both halves are utilized. Then write down both halves of input signal is utilized in full wave rectifier. Whereas only one half of the input signal is utilized in half wave rectifier. Right? So that's why we call it full wave and half wave. Right? That's why we call it full wave and half wave. That's the exact reason behind identifying it as a full wave rectifier and a half wave rectifier. Right? That's the thing. Right. Next. 5. Calculate the mean value of DC voltage, VDC of the rectified signal. Take VDC equals VP into 0.65, right? The equation is given, nothing to do. VDC equals VP 0.65, right? VP is found as 14 before, no? That was 14, right? Then 14 into 0.65, right? That is 9.1 volts, 9.1 volts, 9.1 volts, 9.1 volts, right? Then part B, right? We are moving on to part B. Part B, right? If the load resistance RL is 400 ohms and the Zener voltage VG is 8 volts, calculate the current IL through the load resistor, right? Zener voltage is 8 volts. If the Zener voltage is 8, right, we know when this Zener diode functions in the reverse bias state, right, this keeps this 8 volts across the Zener diode, no? It keeps the Zener voltage across the Zener diode. This RL is now given as 400 ohms, right? RL is given as 400 ohms. Then if I need IL is the current through RL, no? Right? See how easy? IL is the current through RL. Then to get IL, apply delta V equals IR for RL. Then for RL, delta V equals IR. Delta V equals IR. Then delta V is 8, right? We need IL. R is 400. Then IL is 8 over 400. 8 over 400. 8 over 400 means if there is 802, which means 0.02, right? Right, which means 0.02 amperes. 0.02 amperes. Right? Simple as that. Simple as that. Then IL, that's it. Part 2. This is part 1. Right? Part 2. The ripple voltage VR. Ripple voltage. Ripple voltage means in rectifiers, right? When the ripple is formed, right? The ripple voltage means the voltage difference between the ripple, right? Voltage difference between the ripple. The ripple voltage VR is given by VR equals IL over FRC, where IL is the load current, FR is the ripple frequency, and C is the capacitance of the smoothing capacitor. If capacitance of the capacitor is 200 microfarads given, 200 microfarads, calculate the expected ripple voltage, right? Then all other values are known. Then VR equals IL over FRC. IL is 0.02 from here, right? IL is 0.02 from here. And FR, we found the frequency as 100. And capacitance is given as 200, that is in micro 10 to the power minus 6. Right? Simplify. Right? 2 cancels off. And 10 to the power minus 6. 4 minus 2. Minus 2 to minus 2 also cancels. It is coming as 1 volt. Right? Ripple voltage is 1 volt. Ripple voltage is 1 volt. And by the way, this is the last year question, right? Sometimes you might have seen, right? I couldn't tell you. This is the last year question, no? This is 2025 A level, 2025 A level essay, electronics essay, 25 A levels electronics essay, right? So we are discussing the last year question here, right? And some students are like saying that, or they are thinking that what we call the rectifier. Rectifiers are not asking. See, now the last year, this entire essay is from rectifiers, right? The reason was there were like not much questions from rectifiers in the recent years, right? Then some students didn't practice the rectifier, right? And sometimes even some in classes also, right? Teachers also, they didn't teach the rectifier because they are thinking the rectifier is not coming, right? But now last year, this entire essay was given from the rectifier, right? So therefore, when it comes to question patterns, we can't say anything, right? We can't say anything about question patterns. It can be different, right? As professors wish, right? It can be different as professors wish, right? Because they can do anything. They can do anything. That's the thing. Now, from our side, what you should do is you have to practice all question types. Otherwise, without practicing the question types, if you are just planning to sit to the exam, sit for the exam, right? Then it will not be effective, right? Will not be effective if you are planning so, right? Practicing all question types is the safest way to do this from our side, right? Then next triple voltage. Okay. Then part three, draw the shape of the expected voltage waveform of the rectified output after smoothing, indicating maximum and minimum voltage values, right? Now ripple voltage is 1, right? After smoothing is asked, right? See, then V out with time, right? V out with time. Now what happens is, now our initial shape was this, no? To show you the exact correct shape, if I get the guidelines from here, right? See, if I get the guidelines from here, now peak voltage is 14, no? See, peak is 14, peak is at 14, then this is at 14 volts, and ripple voltage is 1 volt, which means that is going to drop up to 1 volt, right? See, that is going to drop up to 1 volt, then 13 volts. So the final shape is like this. Final shape is like this. Final shape is, now it is reaching the peak and dropping up to this level only. Dropping up to this level only. Right? And this gap in between, oh wait, this gap in between is connected by the capacitor. This gap in between is connected by the capacitor. Capacitor variations are linear. Then this is a linear part. This is a linear part like this. And again, from here to up to 13 it drops. From here to up to 13 it drops. From here to up to 13 it drops. Right? This black colored one is the expected voltage variation. Right? Now in the class also we have drawn these ones. Right? Now in this question, something is given as a ripple voltage. Right? That's the equation given for us. Then using that triple voltage equation, then we have to adjust ourselves and do this. Right? So this is the expected curve. This is the expected curve. Right? So likewise, you have to be kind of conscious and very mindful about these things. Four. What will be the ripple voltage if the capacitance of the capacitor is doubled? Right. If the capacitance is doubled, what happens is, right? If the capacitance is doubled, right? What happens is, we know capacitor functions from Q equals CV, no? Right? It functions from Q equals CV. It functions from Q equals CV. Right. Now this is only about triple voltage, right? Yeah. If there is only about triple voltage, you can argue using this also. Right? Because this equation was given. What is the equation given? What was the equation given? VR. Triple voltage is IL over without changing anything else. If capacitance is doubled, simply if capacitance is doubled, VR is halved. Right? If capacitance is doubled, VR is halved. Right? So therefore, ripple voltage is halved. Ripple voltage is halved. Ripple voltage is halved. Right? Ripple voltage is halved. Next, part C. Part C. C1. Describe how to regulate voltage using a diode. Right. Describe how to regulate voltage using a diode. So we know diode functions as a normal diode when there is in a forward bias state, and diode function as a voltage regulator when they are reverse biased. Right. So what happens is, when they are reverse biased, right? When they are reverse biased, it flows a leakage current through the diode by keeping a constant voltage difference across the diode. Right. Since it keeps a constant voltage difference across the diode, voltage is regulated. Right. Write down. Write down. Write down. When it functions in reverse bias state, in reverse biased state, when it functions in reverse biased state, right, it flows a leakage current. It flows a leakage current through senadiode, and keeps a constant voltage difference, a constant voltage difference across it. So voltage is regulated. So voltage is regulated, right? So voltage is regulated. So likewise, write a complete answer. Right? So you know these related theories, no? And when you answer, make it complete. Write it as a complete answer. Right? Otherwise, don't write like what we call the partial answers or the incomplete answers. No marks will be given. Right? See, one is done. Then second one. Given the ripple voltage value obtained in B2 above will smooth using drop below. Given the ripple voltage value obtained in B2 above, will the smooth voltage drop below 8 volts? If so, is the regulation still effective? Give reasons for your answer. Right. So what they ask is, will this ripple voltage go below 8 volts? Right. That was 13. So it won't go below 8. That is 13. No. No. Right. There is no. Right. There is no. And will there is effective? Now about the diode, this is what you should know. Right. This is what you should know. If the voltage difference across diode is less than the Zener voltage, right? If the voltage difference across any diode is less than the Zener voltage, it won't function, right? If the voltage difference across the diode is less than the required Zener voltage, it won't function, right? That is the thing. It won't function. Then, if the voltage difference across the diode is greater than that Zener voltage, it will function, right? It is effectively functioning. If not, it won't function, right? Simple as that. Right now, it doesn't fall beyond 13. No, it doesn't fall beyond 13, which means that is always above 8. Since that is above 8, Zener diode is always functioning. That is always effectively functioning. No, the reason is uh, minimum output voltage. Minimum output voltage is 13 volts. Minimum output voltage is 13 volts. According to above calculation. Hence, voltage difference across. Hence, voltage difference across Zener diode is always greater than 8 volts. So Zener diode functions effectively. So likewise, have complete answers. Write complete answers. Otherwise, don't write incomplete like here and there answers. Right. Part 3. Calculate the minimum capacitance value required to ensure smooth voltage never drops below 8 volts. Calculate the minimum capacitance value required. Minimum capacitance value. Right. Then for that, calculate the minimum capacitance value required to ensure smooth voltage never drops below 8 volts. Right, which means minimum voltage that could go up to is 8 volts. No? If it never drops below 8 volts, then in this curve, right, in this curve, right, as 13 volts, now if it could go up to 8 volts, right, if that is never going to drop beyond 8, right, minimum value can get is 8 volts, right, minimum value is 8 volts. Then if there is 8, say part 3, right, part 3, calculate the minimum capacitance. Yeah. Part 3. Then voltage difference. That voltage difference is the ripple voltage here now in the new circuit. Right, now this voltage difference will be the ripple voltage in the new circuit. Now if this is 14, right, if it is not going beyond 8, then new ripple voltage is going to be 14 minus 6. Then VR equals 14 minus 8. That is 6 volts. Right, that is 6 volts. And the equation was given to us. VR equals IL over FR, right? FR, IL over FRC. Now VR is 6, right? And IL is unchanged. 0.02. Frequency is unchanged. 100 C. Then from this, have to find C. So C is given by 600 here over 0.02. Right, 600 over 0.02. 600 over 0. The other way, right? 0.02 over 600. 0.02 over 600. Then 0.02 over 600. Right? Simplify. 0.02. 2 over 6 is 103. No? Then 600, 10 to the minus 10 to the power 2 here. Then altogether 10 to the minus 4 here. Then this is 0.33, which means 33.3. You can keep it in microfarads. 33.33 microfarads. Right? So likewise, now we are using the same given equation. In this required manner. Right? Now always, if there are any arguments to be mentioned, right, you have to mention all these arguments properly to the point. Right, if arguments are to be mentioned. Fourth, determine the range of resistance values of the safety resistor RS should have so that the Zener power does not exceed 1.6 watts and 8 volts output stays in regulation with 400 ohms load. Take minimum Zener current as 5 milliamperes. Right, now RS is here. Right, now after this point we know what happens is, right, if this incoming current is I, say this current is IL, right, and through this Zener diode another part of the current flows, that is IC. Then it is like I equals IC plus IL, right, Kirchhoff's laws. Right, that is capital I equals IC plus IL. Right, now first part is about right, Zener diode power does not exceed 1.6. Zener diode's power does not exceed 1.6. Does not exceed means that is the maximum value, no? That's the maximum value. Then if we find the maximum current, we know P equals VI. Right, if I need max, then P max, right, equals, this is V max, right, and I max. P max is 1.6, no? 1.6. V max is 8 into I max. Now from here, maximum current through Zener diode can be determined. Then I max is 1.6 over 8. 16 over 8 is 2, then 1.6 over 8 is 0.2. 0.2 amperes. Right. Maximum current through center diode is 0.8. Right. Now, what is asked? Determine the range of resistance values for RS. RS current. Then through RS, do we know the current flow through the RS? Through RS, do we know the current flow through RS? We know, because I is given by IC plus IL, right? That is given by IC plus IL. So we know for the maximum current, the minimum resistance occurs. No? For the maximum current, the minimum resistance occurs. For the maximum current, the minimum resistance occurs. Right. So we know potential at this output here is, right? It was potential at the output. Potential at the output was 14. Then see, you have to identify these values. Then this must be 14. This must be 14. And this is grounded 0. Then this point is also grounded. If this potential difference is 8 volts, then this is at 8 volts. Right? Which means potential difference across RS is known. Potential difference across RS is known. Right? If you need to find a resistance, if potential difference and currents are known, apply delta V equals IR. Right? Then for the maximum I, minimum R comes. For the maximum I, minimum R comes. Right? Then for RS, for RS, delta V equals IR. Delta V equals IR. Right? Then delta V is 14 minus 8. 14 minus 8. And I here is right 0.8 flows as Imax, that is through the Zener diode, and another 0.02 IL was determined before, 0.02 flows as IL, right? Then you have to add both together, then 0.2 plus 0.02, right? Because this is the reason, right? This is the reason. From Kirchhoff's laws, you know, right? From Kirchhoff's laws, you know, I is given by IL plus IC, right? I is given by IL plus IC, right? So I use it here. I used it here. Then this is 6, and here R, sorry, R min comes. Maximum value, minimum resistance. Then this is 0.202 times R min, a small simplification. Then R min comes as 27.3. 27.3 ohms. Right? Minimum R is 27.3 ohms. 27.3 ohms. Alright, 27.3. And then we need to find the maximum value also, right? Maximum value also. Then maximum value occurs when the minimum current flows through Zener diode, no? Maximum value occurs when minimum current flows through Zener diode. Then minimum I is, right? Similarly, now as I found this I, now minimum I is, right? Minimum current flows through Zener diode is, it was given here. It was given as 5 milliamperes, right? Then 5 milli means 0.005, no? Right? 0.005 plus load current 0.02, right? 0.02. Then minimum current here is 0.025, or rather 0.025, 0.025. Then again delta V equals IR for RS, delta V equals IR. Right? Still, delta V remains same because points are same. This is 14 minus 8. And I is this one now, 0.025. R is for the minimum current, maximum R max comes. For the minimum current, maximum R comes. Then R max equals 6 over, right? 6 over 0.025. 6 over 0.025, right? That is 240 ohms. That is 240 ohms, right? That part is also done. That is 240 ohms, right? Now, what was asked from us, right? That was about the range. Range determine the range of resistance. Then you have to mention the range. Therefore, range is right. It varies from now the minimum value was 27.3, right? Minimum value was 27.3, maximum is 240. Then 27.3, sorry, 27.3 ohms greater than RS 240 ohms, right? This is the range. That is in between these two, 27.3 and 240. That is in between 27.3 and 240. In between 27.3 and 240, right? Range is known, right? See how these logics are used, right? My logics are used, and the question is totally different from diodes, normal PN diodes, and Zener diodes, right? So still it is drawn. It is going with the diodes. Part D, right? Part D. 1. D1. If the diodes are not ideal and forward biased, voltage drop is 0.7 volts, what will happen to the triple voltage, right? If these diodes are non-ideal, we know, 1 second, right? We know in the full wave rectifier, right? Even though there are 4 diodes, only 2 diodes are working at a time, no? Only 2 diodes are functioning at a time, right? When this point x is plus, or right, when this above point x is plus, see, when this above point x is plus, right, how current flows is like this, and only this diode is forward biased, and it flows through this, right, flows through this, and flows through these two, and comes here up to this point, and then this was reverse bias, so it goes through this, right, it goes through this, and here, and it completes like this. See, only 2 diodes, these two are functioning now. So likewise, even if x is minus, if that point is minus, right, there will be only 2 diodes which are functioning, which are activating. Then if 2 diodes are activating, there are 2 voltage drops, right? About these voltage drops we discussed in the theory class, right? About these voltage drops. In full wave rectifier, there are 2 voltage drops. In half wave rectifier, there's only 1 voltage drop. In full wave rectifier using centered up transformer, there's only 1 voltage drop, right? We have 3 different rectifier circuits, right? Half wave rectifier and full wave rectifier using bridge circuit, that is this one, and the other one, full wave rectifier using centered up transformer, right? That is the other one. And in the centered up transformer, there's only 1 voltage drop, and in this one bridge circuit, there are 2 voltage drops. Then what happens is, if there are 2 diodes are going to function with 0.7 voltage drops, right? With 0.7 voltage drops, then altogether, if 2 diodes are functions, 0.7 into 2, this voltage will be dropped from the final output. Right? Then the question is, what happens to the triple voltage? Right? What happens to the triple voltage? Then about triple voltage remains same. Triple voltage is the difference, no? Triple voltage remains same, but what changes is the maximum voltage or the peak voltage, right? Then if the diodes are not ideal, what will happen to the ripple voltage? By how much will the peak value of the smooth DC voltage change, right? Then first about ripple voltage, no? Ripple voltage is unchanged. Ripple voltage in the equation again, ripple voltage depends on that equation, right? Then ripple voltage is unchanged. Ripple voltage is unchanged, right? But peak voltage is dropped by 1.4 volts, right? It's dropped by 1.4 volts, right? Drops by 1.4 means it drops up to Calling 14 Adibbe, right? 14 minus 1.4 is it drops up to 12.6. Drops up to 12.6 volts. Right? This is what's happening. This is what's happening. Because two non-ideal diodes are activated now. Two non-ideal diodes are activated. Two non-ideal diodes are activated. They absorb two voltage drops. Right? They have two voltage drops. Second one. How does a Zener regulated DC voltage respond when a load resistance is decreased? When the load resistance is decreased, right? Now the thing is, right? Now the thing is, what is going to change? Zener regulated DC voltage respond when the load resistance is decreased. Now, main feature about a Zener diode is Zener diode does not change its Zener voltage even though the current through Zener diode changes. Right? That's the main feature of a Zener diode. Even though the current through Zener diode changes, VZ Zener voltage is unchanged. That's the unique feature, most unique feature about a Zener diode. Right? Which means now even though the current changes, right? Even though the load resistance changes, when load resistance changes, current changes. Right? Then IZ will also change, but yet VZ remains unchanged. That is the most important feature and the unique feature. Important means unique feature about a Zener diode. Then this is what happens in the circuit. Right? This is what happens in the circuit. In the circuit, right, when RS changes, right, IL changes. RS decrease RS decreases. See, when RS decreases, right, when RS decreases, right, IL increases. When IL increases, IC Zener current decreases. Right, Zener current decreases. Right, but right, VZ is unchanged. But VZ is unchanged. That's the unique feature about the diode, right? But VZ is unchanged. Then the question is, how does regulated voltage respond? Then you have to explain this. For the load resistance when decreased, then you have to explain this way. Explain this in words. When RS decreases, IL increases. Hence, IC means Zener current. Zener current decreases. Zener current decreases. Right? But Zener voltage remains unchanged across the Zener diode. Right? That's the most important feature about a Zener diode. Right? Zener voltage remains unchanged across the Zener diode. Right? That's it about that question. Right? That's it about that. Right. Listen now. I will keep question 2 as a homework, so you can try it later. Right? You can try question 2 later. Right? That is also like basically that is from op-amps and flip-flops. Right? Op-amps and flip-flops. And about the electronics as an overall. Right? About the electronics question as an overall. Right now. About the electronics question as an overall, right? About the electronics question as an overall, right? These are the other main parts you need to check for. Listen, about the electronics question as an overall. Right now, today we got to know some idea about starting from op-amps, starting from JFETs, right? First, we got to know about JFETs, right? These ones you got to know: JFETs, op-amps, then some digital part, right? Digital means it was only logic gates, right? And finally diodes, right? And the other parts you need to check here, right? You need to practice here before going to the exam is, right? Before going to the exam is bipolar transistors. Now today I discuss about a unipolar transistor. No, practice bipolar transistors, right? And then few more diodes questions, right? Bipolar means NPN, PNP, NPN, and PNP, right? And when comes to unipolar transistor, then unipolar transistor, right? Here we have NJ FET, right? NJ FET, right? And TJ FET, NJ FET and TJ FET, and in NJ FET, right? In NJ FET, right? The regular circuit and the voltage divider, Now here also you have the regular circuits. Regular means common emitter, and the other type is voltage divider. Right? Both questions are there, both types are there. And then about op amps, right? About op amps, right? About op amps, non-inverting, operational amplifier, right? Then inverting operational amplifier, right? Other than that, differential amplifier. All these questions are done in the theory class. Practice more questions, right? Otherwise we have done all these question types in the theory class, right? Differential op amp, differential amplifier, differential op amp or differential amplifier, and then summing amplifier, summing amplifier, right? Then voltage follower, and other than that, this is about closed loop, no, right? Now all these ones are about closed loop configuration, right? They are closed loop. And from the open loop, right? Right? From the open loop, right? Variations, right? And especially LDR, IR, PD circuits, right? So these are the other parts you have to look into, right? These are the other parts you need to look into, right? Before you are going to the exam, if you are planning to take the electronics integration, right? And as an overall, this is undoubtedly the question that you can complete in the least time, right? That is the main advantage we have. That is undoubtedly the question we can complete in the least time. So if you are 100% familiar, right? If you are 100% familiar with the op amps, with the electronics, right? You can get this question, you can touch this question without any hassle. That's the thing, right? So practice these question types, right? And practice what is coming, what has come in past papers, right? And practice few more questions, right? Now we have come to the end of the session I planned for today, right? If there's anything, any questions, any clarifications needed from my side, you can ask, right? If any questions or any clarifications needed. And so likewise, as I took electronics today, right, I'll be taking the other special essays we have in our paper in the coming sessions also, right? So you can get all updates through the channels. And on the next S2A, right, I'll be finishing the support seminar MCQ paper, right? We have discussed 25 MCQs only last day, right? And Then I'll be completing the rest, the 25 MCQs of that support seminar paper, right? And provincial papers are also out, right? So you can try those provincial papers also, right? They are out, and I'll be discussing some provincial papers also, right? There are like 8 provincial papers out now, right? Then yeah, those are the things happening. Those are things happening. Any questions or any clarifications needed from my side about anything, subject matters, or the things we discussed today, or anything like that? Do similar ones for waves, current, electricity, and few others. Yeah, I'll be taking all special types of essays we have, right? I'll be taking all special types of essays we have, right? Right? Special types, and the essays that you can score easily, right? I'll focus mainly. Anything else? Anything else? Anything else? No? Are you all good? Right. Then, if no questions and if you are all clear, right, we can wind up for today. Right, we can wind up for today. So likewise, practice these writing essays. Practice this. And now today I gave you the idea how you should write. That's the thing, no? How you should write with the arguments. Right, mentioning arguments is mandatory. Right, otherwise, even though your calculations are there, without arguments you won't get marks. Right, if you are using any kind of laws, logics, right, or any kind of a rule, something like that, everything should be mentioned. Everything should be mentioned, right? And especially when it comes to questions like, current, electricity, electronics, right? When you apply voltage dividers, potential dividers, uh, delta V equals IR, right? So likewise, mention to which resistor you apply. Mention to which resistor you apply. When you use Kirchhoff's laws, mention to which loop you use, right? So likewise, be it very clean and tidy. Be it very clean and tidy. Keep it very clean and tidy, and follow these things. Follow those things. Those are the things, especially about current, electricity, electronic questions, right? When you are marking currents in the circuit, right, mark it correct, right, with the correct directions. And when you mark a current, don't just use an arrow, right? Label it, right? And when you are marking potential differences, use 2 letters for the potential difference. When you are marking points, use letters, right? Use English letters for the potentials, and for potential differences, write the difference like VAB, VBE, right? VCE, VBC, likewise VGS, VDS, likewise use those letters accordingly, right? So likewise, those are things, right? Keep them in mind. And with these learnings you got today, right? Practice few more questions. Practice more questions, right? So basically, when it comes to parts like electronics, right? About electronics, there are few theories, and electronics is mainly driven using current, electricity, right? Only about electronics, there are only few theories, because electronics is building up on electricity, right? So everything we do, marking currents, Kirchhoff's laws, current divisions, delta V equals IR, potentials, potential differences, everything, right? They are on current, electricity. They are current electricity. And above that, there will be some other special theories, right? Special theories for electronics. Now, for bipolar transistors, there are some specific functioning and specific theories about the bipolar, right? For unipolar transistor, some other specific theories. For op amps, specific theories. Likewise, they are very small parts, right? So you can integrate those things, right? That's how it should do. You have to integrate those things with the current, electricity baseline we have, and we'll be using both together in questions, right? We'll be using both together in questions. That's how it goes, right? Right. Then, if no questions, we'll wind up. Practice more questions, right? 25 days. Practice more questions. Work hard, right? Work hard and invest this time. This is the golden time you got in your lifetime. It's a golden time, right? Then don't waste it. That's the point. This is a golden time. Don't waste it. Okay. Then see you in the next class or in the next session. Right? Then work hard and stay safe. Good night and goodbye. See you.